Welcome everybody again, and we can finally begin our discussion on organic chemistry. And I would like to start our discussion on organic chemistry with a very important topic that we're going to see throughout the entirety of the course. And that is something called resonance structures. Now you might be familiar with resonance structures from your general chemistry course, but I'm going to go more into an in-depth detail of resonance structures here because they are very, very important in organic chemistry, and understanding them will really help you get a better idea of organic chemistry and the reaction mechanisms that we're going to study in the future. Now, a resonance structure, I have the definition over here, two forms of a molecule where the chemical connectivity is the same, but the electrons are distributed differently around the structure. Now, I'm going to explain this definition by showing you examples so that you can better understand what resonance structures is, so don't worry if you don't quite understand that right now. And before I actually dive deep into resonance structures and how to do them, I'd like to talk about two things. First, the kind of notation that we like to set for resonance structures, and then something called curved arrows. So as you can see, I have an example over here of an organic compound, and we have a double bond and a positive carbocation. And remember that this positive formal charge simply just means that the carbon has 3 bonds on it with an empty p orbital, and if it was a negative, it would be 3 carbon bonds and then another fourth bond. But it's not really a bond, it's just still kind of a lone pair hanging around. So that's what a negative formal charge would be in a positive. I'm not going to calculate the formal charges. I mean, you can pause the video and work on the formal charges yourself, but eventually you'll get good enough where you won't need to do that anymore. So first I'd like to talk about the notation. Well, I'm just going to draw the resonance structure of this as it is, and if you don't quite understand where I got it from, don't worry. I'm going to cover how I know that that's the resonance structure for this upcoming soon. So right now, just kind of focus on the notation that I'm doing, and we should be good. So that's the resonance structure of this. So what I really only want you to know, forget about this for now, how I have this arrow notation and everything in parentheses or brackets. And now this arrow does not mean like in equilibrium where you have a half reaction arrows going forward and backwards. That's not what it means. It just kind of says, well, this is just the resonance structure of this. They're basically the same molecule with the different connectivity of their atoms. And now what I'd like to focus my attention on is this curved arrow that I have. Now this curved arrow is going to be very important. You're going to see it all the time in organic chemistry when you get to reaction mechanisms. One thing I'd like for you guys to understand now is this curved arrow here does not represent the movement of electrons when we're dealing with resonance structures. Yes, we are moving the pi bond there and the electrons there, but in an actual reality, it's not the electrons that are moving. It's just a tool that we are using for resonance structures. Once we actually get to reaction mechanisms and I draw curved arrows there, then that will represent the motion of electrons. So the curved arrow, as you can see, this point right here represents where the electrons are going. Remember, in reality, they're not actually moving. This is just a tool that we use for resonance structures. And the end kind of shows where they're going from. So exactly as it is, this moves there, and that's indeed what happens there. And you'll understand why this positive carbocation will move over there and stuff like that during resonance, and why I specifically chose to move this bond there later. Right now, we're just going to worry about curved arrow. And there's these two kind of rules that I'd like you to know, and they're super important, so I'm going to actually write them down as we go along instead of having them already pre-written for you guys. So the first very rule is that we can never break a single bond. And as an example, I can give you, let's say we were given something like this. You can't just say, oh, well, I'll just break this single bond and move it there so that I'll just have this right over here. So I'll have this. This is wrong. We don't want to do this. Never break a single bond. And the second rule is never exceed the octet rule, as I covered before in my general chemistry review video, for second row elements. And what I mean is, as an example I have over here, let's say we have something like this. So I can't just say, oh, well, I'll just take these electrons and put them over there and I'll have something like this. Because if we did this, carbon exceeds the octet by having 5 bonds, and we know that this is not true. So once again, we can't do that because carbon has 5 bonds. So these are the two kind of important rules that we should remember, and these, you'll never, ever, ever have to worry about breaking these rules if you just learn to memorize them. So very important, never break a single bond, never exceed the octet rule for second row elements. So now that I've kind of explained the notation for resonance structures and kind of these curved arrows that we use to show resonance structures, as well as the two kind of rules that we should know, I'm going to get into resonance structures. And now this is where you'll start to understand how I knew this was a resonance structure and this was indeed the curved arrow I was supposed to use to form this. So there's these kind of 5 patterns that you follow throughout, and I'd like to begin with the very first one over here. So the first kind of pattern we have right over here is an allylic lone pair example. And you might be wondering what allylic or allylic means. I don't quite really know how to pronounce it that well, so pardon me for my pronunciation. But basically what this word means over here is, as we can see, I've taken the liberty of drawing a molecule right here. It doesn't really matter what molecule it is, but we see a carbon-to-carbon double bond. And this is what we call a vinylic position, once again, pardon my pronunciation. And everything that's attached with this position are the allylic or allylic positions right over there. So that's what I mean. So as we can see, I have these kind of 2 structures, and we're going to draw their resonance structures. So as you can see over here, this is our vinylic position right over here, because it's that carbon-to-carbon double bond, and what exactly is attached to this right over here is an allylic position. Now there's also 2 hydrogens are coming out from here that are not shown that are also allylic positions, but this talks about an allylic position with a lone pair. Only this side has a lone pair, so that's how I can distinguish that this is one of the patterns for resonance. And essentially, all that happens over here is that you're going to take one of these double bonds and you're going to kind of break it by pushing the electrons outward over there. And once we do that, you push these electrons to form a double bond. So you're kind of breaking a double bond and forming one at the same time. And this kind of ensures that we don't break that octet rule. So as you can see now over here, when these electrons get pushed out, I have a lone pair attached to it. That's where I get that negative. You could even do a calculation with the formal charge formula from the previous video to understand why that's a negative, but hopefully this is sufficient enough. And from here, you're making this double bond. So you're kind of breaking and making a double bond. So if I look over here in this one, well, I have this allylic position right over here, and what I want to do is I want to use it to make a double bond. So making a double bond, and remember, if we want to obey the octet, we got to make sure that we break this by moving the electrons outward so that our rule of the curved arrows is properly being used. So, and exactly what I'm going to have here is this. And it's very important that you do show these plus and minus formal charges, because this is a plus formal charge because the oxygen now has 3 bonds in 1 lone pair. If it had, let's say, 3 lone pairs in 1 bond, it would be a negative. And then if it's 2 lone pairs with 2 bonds, positive. You kind of will start remembering that, so you won't really have to keep using the formula again and again. But essentially that's what happens. You're basically forming a double bond with the lone pairs and then breaking one. And this formation of that double bond is coming from that allylic or allylic position. And then you push the pi bond out here to create this negative formal charge molecule with the lone pairs outside. So that's our first pattern of 5. Our second pattern is the allylic positive charge. So as you can see, it's the exact same concept as the last one. So this is your allylic position because it's attached to the vinylic position because of this carbon-to-carbon double bond. Now there are these also 2 hydrogens that are in the allylic position technically, but we don't care about them because we're looking for the allylic positive charge, so we're only considering this side. And basically what's happening over here is that we're basically just moving this pi bond to this side in this kind of pattern that creates, it just moves the double on the other side, and then your positive formal charge just switches to the other end. So that's how I knew in the beginning example that that was a resonance structure, because I had realized it was an allylic positive charge. Now, our third kind of pattern for resonance structures is a lone pair adjacent to a positive charge. Now, the word adjacent, if you're not quite familiar with it, just kind of refers to neighboring. And, well, if we look over here, there's a positive charge right here, and right beside it is this oxygen molecule that has lone pairs. So there are indeed lone pairs that are neighboring to this positive charge. And I've already taken the liberty of drawing this resonance structure out beforehand. Basically, what the lone pair will do is it'll form a double bond to take out this positive formal charge, because now carbon has 4 bonds. Notice how originally this was a positive because there was no hydrogen bonded here. That's what made this positive. If there was a hydrogen not being shown bonded, we wouldn't have this plus charge here. So that. Now in this example right over here, we have a positive charge, and yes, neighboring it is an oxygen with a lone pair. Now this might not always be an oxygen, it could be a nitrogen or something with a lone pair, but that's just basically the purpose of this. And what's going to happen here is that this lone pair is basically just going to form this double bond right over there, and now this will now switch, and the positive formal charge will just come over there like that. And you could redraw these out in normal line diagrams to double check if this verifies the octet. So that's what I used to do when I was quite new to these. So I would draw this out completely with the carbons and all hydrogens being shown, then I'd move the arrow, and then I'd be able to verify, yes, the octet rule is being obeyed, and yes, I'm not breaking any single bonds. And then once I had that final product, I would just convert it back to a bond line structure. That's a good way to start practicing, but once you get better, you'll be able to directly go from bond line to bond line without having to worry about that. So our actually, before I go into my second last resonance structure pattern, I'd like to talk about this example above over here. Now, this example, as we've seen in the last two examples, we've only had one arrow being used. So as I see over here, I have a positive and then a neighboring lone pair from over here. And now what's going to happen is that this neighboring lone pair can donate, since it's a negative formal charge, it can donate, once again, its electrons over there to form that double bond. Now, if I were to just write that, and then just write my double bond of oxygen over here, which I'm not going to do, I would be wrong. And why I would be wrong is because now nitrogen has 5 bonds to it, and that's not possible. So this is an example of where the octet rule is not being, we're exceeding the octet rule in this case over here. So what I'm going to have to do is I'm going to have to think of a way of moving one of these bonds so that even nitrogen will have its 4 bonds. Now, I can't break a single bond, but it doesn't say anything about breaking a double bond. So what I'm going to have to do is I'm going to have to push the electrons from one of this double bond outwards. So what I'm actually going to get left with is now an oxygen with 3 lone pairs, which will give it that negative formal charge. So don't always just assume, oh, well, there's only one arrow drawn in the example, so therefore we're always only going to be drawing one arrow. No, you should always double check for if you're ever breaking a single bond or exceeding the octet. That's very, very important. So yes, once again, in this example, we had to use 2 arrows because the octet rule was not being verified here. We were exceeding the octet and giving this more bonds, 5 bonds to be precise. So that's why I had to push it out. And once again, we can't break single bonds. So now I'm going to move on to the fourth kind of pattern we have, and that is a pi bond between 2 atoms of different electronegativity. So basically, a good example that most likely you're going to see most of the time that I can think of, that I could think of off the top of my head, was a carbon to oxygen double bond and a double bond with nitrogen and carbon. So in this example over here, we have that carbon to oxygen double bond. Now, carbon and oxygen, we have that double bond, but also the electronegativities are different. Oxygen is way more electronegative than carbon. So that's how I can tell that this is going to be a pi bond with 2 different atoms of electronegativity. So because there's that double bond in the carbon oxygen, and oxygen is more electronegative. So all that happens here is that we break this pi bond by moving the electrons out to the more electronegative atom. hence why the bond between atoms of two different electronegativity pushes to the more electronegative atom, which in this case is oxygen. So one, and now since the electrons are pushed out, I have another lone pair giving this a negative formal charge, and now I have an empty p orbital, a carbon with an empty p orbital, so carbocation basically, and I got a positive charge right over there. So that's how we work with pi bonds between two atoms of different electronegativity. And now the last one, which I would like to think is the easiest one, is conjugated pi bonds enclosed in a ring. So you're only going to see this in ring systems, especially reactions with benzene and stuff. And basically this is the easiest one. All that happens is you got this pi bond that moves over, this pi bond that moves over, and this pi bond that moves over in this ring. So this and this and this, and that's it. So these are the 5 patterns that you're most likely going to come across in organic chemistry, but those examples were kind of easy and straightforward because I was directly stating, well, this is what pattern it is and yada yada yada. But most times you're not going to be told what pattern it is. You're just going to be given a structure, and you're going to be asked, hey, draw the resonance structure for this. So I've taken the liberty of getting these examples right over here, and what I'd like for you to do is to write them down, pause the video, and work on them. And then unpause the video and see how I do them and verify if you get the exact same answer or not. So pause the video right now and do some examples. Okay, well, I hope you guys paused the video and at least attempted to try to do the examples. So now I'm going to work on them with you guys. So let's look at this very first example over here. What we have is this, and we're asked to draw its resonance structure. The first thing I like to do is I like to think, what pattern does this exhibit? Well, what can I see here? The first thing that I notice is I see a carbon double bonded with an oxygen. And that instantly tells me I have a pi bond, and I know that carbon and oxygen have different electronegativities. So I didn't really write the formal charges. I should have over there. So I know that this is automatically going to be the pi bond between two atoms of different electronegativity. And what I know is that I can basically just move this pi bond, take the electrons and move them upward. So if I do that now, what do I get? I get this structure right over here with its negative formal charge. Now, I'm not done yet, and you might be wondering why. I'm not done because this carbon had 4 bonds, but now it only has 3, which means that this is getting a positive formal charge because that has that empty p orbital. And now I can be like, okay, is there any other pattern exhibited that I could kind of show for this? And well, what I see is I can see that this does have indeed an allylic positive charge because I have this vinylic position right here, and then a positive charge that's directly in the allylic position that's directly beside this vinylic position. So I know that I do indeed have another pattern. And what I know from this pattern is that this double bond will just move over there, and it'll basically just take my positive charge and move it over. So there. And we don't really need to draw anything else because if I were to do this exact same pattern I did over here again, I would just get left back with this again. So that's how I know I'm done. Now for the next example, first thing I do is recognize what pattern this is, and well, I do see an allylic position with a positive charge. So like in this example, that's the mechanism that I'm going to go by, and I know that this will just move the pi bond over there and my positive charge to the next carbon over. So I have that, and now I'm not done again because I can do, if I move this, if I do the allylic positive charge pattern again, I'll get with this side, I'll get left back with exactly what I had. But if I do the same thing again on this side, I'll get something different. So once again, it can move over like that, and I get my plus charge right over there now. And once again, if you're kind of still confused, you can always switch back to your normal structures, line structures, where you have everything being shown, and then you can see from there if the octet's being verified or not. But I assure you it is in these examples. So now in the next example, once again, let's see what pattern. Well, I see in the allylic position and I see a negative charge. So I know this is in a like lone pair pattern recognition. And what I know from there is that basically this negative here, just I didn't really draw them in before to kind of trick you guys, but this does indeed have that lone pair, and the lone pair is going to move itself over here. And what I have to remember is if I move this lone pair over here, I have a 1, 2, a hydrogen not being shown, and this right over here. So if I move it over here, I have a hydrogen, I have this carbon right over here, and I have a double bond here. But remember that we need to make sure the octet's verified over here, so I'm going to have to push that lone pair, this electrons out to form a lone pair. So what I'd get left with now is something like this. And then I'd have the negative lone pairs and the negative charge of the lone pairs pushed out like that. And now in the next example, I see once again the same thing as the very first example, a carbon to oxygen double bond with the lone pairs over there, and I know this is going to be the pi bond between two atoms of different electronegativity, and I know what's going to happen here is that this is going to push and break that pi bond, so we're going to form a negative formal charge over there, and then I have remember, I can't forget, I have to put a positive charge there because originally carbon had 4 bonds here, and now when one of the bonds move, it becomes 3 bonds now, like that, with no lone pairs, so that's why it's that positive charge. And now what I'm going to have to do is, I'm going to see, is there any other pattern I can do? And, well, what I notice here is I do have a lone pair adjacent to a positive charge. This positive charge is being neighbored by the oxygen's lone pair, so what I can do here, I know, is I can move the lone pairs over here. So once again, if I move them over there, so I didn't do anything over here, so this stays the exact same. And now I have a double bond over here, and I know that this oxygen now only has 1 lone pair, and since it's 3 bonds on that oxygen with just 1 lone pair, I get a positive formal charge over there. And I don't see any other pattern, so I know that that's that. And now the very last one I see over here is the exact same thing. I see basically a lone pair that is adjacent to a positive charge, so this positive charge, and neighboring it is the oxygen's lone pair. So I know what's going to happen here is that we're going to move this lone pair down here. So that's how I form this double bond. And now I have that, I know that there's only 1 lone pair left, and I'm going to have a positive formal charge on this oxygen. And I don't see any other patterns exhibited, so I know that that's that. And so those are the resonance structures for those that I had. And like I said, you probably might not see all of these resonance structures, but you might see some of them. So it's always good to understand resonance structures and understand where I'm getting all these curved arrow notations from and why I'm putting them in specific places. But I guess that's it for resonance. In the next video, I'm going to talk about resonance stabilization, so how we can determine what resonance structure would be better than the other. And then from there, I'm going to start more into acids and bases and talking about acidity and qualitative and quantitative analysis. So if you have any questions, concerns, comments, you can email me. My email will be in the description down below, or you can comment. And don't forget to comment, rate, and subscribe. And I hope to see you guys again soon. Thank you.